Hello YouTube, De-bodgery here. Welcome to EV Components Review. On the bench is a KVD7245, which is a 90 volt max, 100 amp max trapezoidal controller from Kelly. We're looking at the CPU right here, so that's CTAG1549, and that is an ARM processor. And I looked that thing up, and it is actually an LPC 1549. And yeah, it's basically 32-bit ARM Cortex M3 microcontroller, 256K of flash, and 36K of RAM. It has USB, CAN bus, it's got a UART, it's got an I2C interface, things like that, all on board. So it's got the full CAN bus package built into it, so you won't find a CAN bus chip on here. Probably in this connector right here is probably the UART and maybe I2C, maybe CAN bus is in there. I can't be really sure what all is in there. I don't remember what the cable pinout is, if CAN bus comes out or not through the cable, but yeah, that's probably what that is. And you can see this one, this label is JSWD, so probably that's some kind of an I/O connector as well. Yeah, you probably either have either you can get to the UART through here and then do firmware flashing from there or something like that. Like when you originally build a board, or maybe that's done to this little 6-pin header, but that's basically what's there. This right here is one of the 3 gate drivers. So as you can see, that's an IR26 or 25602, and that is a 600 volt max half bridge driver from International Rectifier. Usually you can see the little logo, the I diode R logo. That's International Rectifier. Fairly common part used. I've found this this little MOSFET driver on other controllers. Seems to get a lot of use. So right there, one board, stand up. So I'm holding this board at an angle because I can get better lighting on it, so you can see the part numbers. Whereas if I lay it horizontal and point the camera straight down on it, that's not so good. So let me prop this up like that. There we go. Yeah, you can see it on there. So yeah, so that says 2902, L2902, this little package right there. And that is a quad op-amp package. Yeah, that one's got a TI logo on it. And yeah, that's just a quad op-amp. So, there's little signals need to be made bigger before they make it over to the CPU. Or maybe it's just acting as a one-to-one buffer, something like that. So there's something like a little bit of protection between the high voltage side and the CPU to help protect things a little bit. But that's basically what the little op-amp package is doing. And this is something that's on here that I thought was super cool. So you can see it says 12 volts, 12 volts, 5 volts, 5 volts. So this is a 7812. These two packages are these little transistor looking things. And these right here are 7805 linear regulators. So probably those two linear regulators are for providing 5 volts and 12 volts to the connector right here for external stuff. And probably 12 volts and 5 volts here are for powering everything on board. So like the MOSFET drivers, they're probably all running off of 12 volts. Maybe this op-amp package is as well. And then 5 volts is probably run the CPU. There's no linear regulator here for 3.3 volts, so that guy is definitely not running from anything other than 5 volts. You can see this connector right here. Yeah, you can see its height. So that's where the little DC to DC board plugs in. And you can see that transistor right there. So it's a D363. That shows up nice at a good little angle here. It gives me some better contrast on the parts, so oftentimes you can't see what they are. And that is a black and white TV horizontal deflection output transistor. Yeah, I thought, okay, well that's interesting when I looked it up. It's good up to 300 volts and 6 amps. So it's definitely got the voltage capability sufficient for the job. And it's acting in a DC to DC converter package, and it's a fairly high frequency transistor. So rather than using a special buck package that has a MOSFET in it, they did it with this NPN transistor instead. And right below it you can see this little 100 volt electrolytic capacitor. And then let's look at the DC to DC board. Pull this aside. So here is that. And again, it's got another 100 volt capacitor on it. You can see the inductor, and then here's your little buck chip on there. And that little guy is, hold on a second. There it is. That's a TPS 5401. I don't know why it shows up on camera, but it does say 5401 on there. Yeah, I can't really see it so well. But anyway, yeah, that little guy right there, that's doing all the oscillator stuff, but it doesn't have any drive electronics in it. So that's what that NPN transistor is for. That's providing the current control part of the whole entire DC to DC. Sort of an odd design that you have this stuff right here on the board. So that transistor, this capacitor, and then that little board, all making up a single DC to DC converter. Why they didn't just put it all on this little daughter board, or why they didn't just populate everything all right here on the main board, doesn't make any sense to me. So this is kind of overly complicated. Yeah, that's sort of strange. I wouldn't have done it that way myself. I'm guessing that they had a bunch of these things made up for a bunch of different other controllers or something, and they went, yeah, let's just keep doing the same thing. I mean, this is a Chinese controller, so that wouldn't really surprise me. China does a lot of things like that, where they just said, you just keep doing the same old, don't ever bother fixing anything. And that may be the whole reason for this, because I'm pretty sure I've taken apart a Kelly controller like a year ago, and I'm pretty sure I saw this same little board in there, and another little transistor off to the side that was all part of the DC to DC converter. So kind of a weird design. Yeah, what were they thinking? Why did they do that? Doesn't make a whole lot of sense. Yeah, it would have been so much easier just to make a little DC to DC board. Literally, that physical size would have done the trick. And in fact, you'd even only need 4 pins. So you need battery minus, battery plus, going in, and then you need 12 volts and battery minus coming back out. So 4 pins had done the trick. 3 pins would have worked. But yeah, sort of strange. Yeah, but that's the Kelly way, I guess. All right, so you can see right there, and also right here, you have some smallish ceramic capacitors for high frequency filtering on the battery bus. And then also in between all of the transistors, you can see these little ceramic caps. Those are also for high frequency filtering on the battery bus. So it's nice to see them right at the MOSFETs like that. That's very much like how the real design work, Trampa, that Benjamin Vetter does, have them as well. It's just that these are a lot smaller. But yeah, the location is pretty darn optimal. So I definitely like seeing that. Just wish they were bigger. You can see the 100 volt, 220 microfarad capacitors there. And I don't know if you can see it or not. Nope. It must be on the other side. Yeah, there it is. Yeah, 80 volts. Why would you put an 80 volt capacitor in a controller that can see a maximum of 90 volts? That doesn't make any sense to me. But hey, there they are. I didn't make it up. Oh, where'd that come from? Washer got jammed in there. I'm sure that is from me. Yeah, the little bugger's in there. Oh, that's my that's my thermistor. Yeah, now I've got it jammed in there. But anyway, yeah, that thermistor it goes over to here. I put some silicone around the two wires because there wasn't anything securing them. They could bend and slowly break off, so now that won't happen. Yeah, now I've kind of jammed my thermistor and I'll have to get that back out again. It's stuck on there now. Oh well, oops. That'll get fixed. Yeah, there we go. Now it's come loose. But yeah, I kind of stuck it in here just to get the wire out of the way. Anyway, that's pretty much... Oh, forgot a part on here, I think. No, I didn't. I mentioned the 2902 already. So that's pretty much everything on here to look at on the top of the board. Nothing else really special. Yeah, that pin header right there might be like UART or CAN bus or something like that going into that chip too. Yeah, you've got 3 separate sets of pin headers here for something that goes back over to the CPU. Just don't know what. Alright, let's flip this thing over and look at the other side. Alright, I do like all of those vias. So Kelly went and did a really good job here on this. You know, this is mostly about a thermal path. So let's flip the board over just a second. So there we go. There's the top side of the board. And this is your phase bus right here. And you've got this whole entire square of copper here. And then a gazillion vias through it to another copper pad that's also phase bus. So that's better than what ASI has by a lot. You know, they just have a single sheet of copper, you know, one layer of it on the surface of the board for their phase buses. And here you've got this on both sides and tied together by 1001 vias. And it's also tied together onto these little aluminum blocks. So yeah, just a really, really good phase bus in there. This isn't really so much about current carrying in here. That's mostly what the aluminum blocks are doing. But all those vias are acting as a heat path from the top side of the board where the aluminum block bolts down to here and transferring heat through all those little copper vias all the way through to the heatsink, which is the bottom of the shell. So that's super good. You can see that they've got 4 current limiting resistors for the MOSFET gates for each one of the MOSFETs. So that's super good. And I think I forgot to mention it up top, so I'll talk about that right now. Yeah, there we go. You can see that one right there. So also on each MOSFET gate drive, so these 4 MOSFETs are in parallel, they also have a small ceramic cap on them, and that's something that's fairly common. You'll see either 1 ceramic cap or 1 per MOSFET gate, and that's basically doing high frequency filtering. See all the crud in here? That's basically a silicone caulk. The whole entire board was coated in this silicone that's still on the faces of these MOSFETs. But yeah, most of it I got it up already. Anyway, that little capacitor, that's for high frequency filtering, or it also can serve another purpose, and that is to slow down the gate drive just slightly. They'll serve one of those 2 kind of purposes. Just kind of depends on where it is exactly in the circuit. So if it's like in what is it, series, I think, with the current limiting resistors, then it's going to slow down the gate drive a little bit. If it goes from the gate leg to like battery minus, then that's high frequency filtering. So I don't know which one that's doing. I didn't bother checking, but that's what that's about. As you can see, these MOSFET legs, they are the TO220 package, and you can see that they're using the skinny portion of the leg, which I don't like to see. And then there's also no solder flowed up onto the leg from the solder pad either. So that's not so great. At least with like ASI, they do the same thing. You know, they're using the skinny portion of the leg, which is suboptimal. But at least they have solder flowing up onto the leg from the solder pad. So you get the best case scenario you can get out of that. And here, Kelly didn't even do that. You only have solder on the bottoms of the legs here. So this is less good than the way ASI does it. But, you know, you're already using the skinny portion of the MOSFET leg, so I guess it doesn't matter too much. Now you're looking at one of the battery minus buses for these 4 MOSFETs. So those are the 4 low side MOSFETs. And you can see all these vias across here so that they have a good current path top and bottom. to those legs, and you can see that there's a little bit of a trace going right up to that leg, and you can see it on that one there, and that one there, and that one there. So yeah, that's a pretty good current path to the MOSFET leg that's going to be on the battery minus bus, and you don't have any path here to get to the phase bus on the bottom side of the board, because that would be this center leg right here that would connect over to here, and well, you've got two little traces in the way, so that doesn't work out. But it is on the top side of the board, so that's good enough. And that's every bit as good as the way ASI does it. And so like from here, you can see that this MOSFET leg, that one, that one, and that one do go right into this copper pad. And then here's battery plus right here, and again you've got two little circuit traces right in front of them. So this center leg, which would go to here, does not have a current path. But that's not really so important, and the same is also true for here. So the current path battery minus is to this leg right here, and then this leg right here is actually the tab on the center leg on the MOSFET. There we go. Center leg on the MOSFET is electrically identical to the tab on the back, and of course these are screwed down to the aluminum block. So this is less important of a current path than this is. This is your primary current path, and those are all screwed down right to an aluminum block. So that's going to work out pretty good. And then this is kind of supplementary, you know, as far as that center leg getting over to the phase bus. And we should be able to see that, I would think. No, I can't really see it underneath the silicone that's still left in there. But yeah, you can. You can see it right there. You see that center leg goes right over to here. So yeah, that's connected to the MOSFET center leg just like it should be. So yeah, that's making a good current path over to here. You know, this is every bit as good as the way ASI does it. In fact, better, because this is double-sided board, and it's got all these vias tying in it, or you know, circuit trace on double sides of the board, and all these vias tying it together. So this is a pretty darn good current path all by itself, and then it's got the aluminum block screwed down to it as well. So yeah, this is a pretty solid, pretty stout phase bus for sure. I don't like seeing aluminum screwed down to copper traces, but then again, this does have solder tinning on it. So the reactivity of aluminum to copper is pretty much mitigated by that, and that's basically the same thing that, like, say, far driver is doing. You know, you've got a thin layer of another metal that doesn't react between the two to make sure that the copper and aluminum don't react with each other. But yeah, that's a pretty decent phase bus, and the same thing for battery plus. That's a pretty solid battery plus bus. Battery minus bus is the same way. You know, and then of course you've got a big hunk of aluminum that sits on top of all of them as well, and you know, two sheets of copper top and bottom tying this all together. This is a pretty decent phase bus without ever even having the aluminum, and they have the aluminum. So yeah, it makes for a really good phase bus. You know, this is a better phase bus than ASI does, and you know, it's a similar design as ASI. So I would definitely like this more. Anyway, I think that's probably everything I have to show on this controller. I did look up this little 6-pin part, so you can see it says, whatever that says, 3564 on it. And I don't think I found it. Let me look real quick. But I'm pretty sure I did not find it. I didn't. Okay, well, yep, that's everything on here. Hope that helps some folks out. Enjoy. And hopefully I'll get another Kelly controller we can take a look at. I'd like to see like an 8080i to see what's different about those, because those are supposed to be a field-oriented control.